Hey everyone, welcome to my channel. So today we'll be learning about the vector operations. So we'll be exploring vector addition, vector subtraction, dot product, and relation between the angle between the two vectors. So first of all, we will be starting with the vector addition. And in the vector addition, there are two methods, the algebraic method and the geometric method. So first we'll be starting with the algebraic method. So I am creating two vectors here. So let me create a vector A having the component x1, x2 and x3. So if you can see here, this vector A has a three-dimensional component. So this vector is in three-dimensional space. Okay, so it has three vector components: x component, y component, and z component. Now I'm creating the vector B, that is y1, y2, and y3. So if I add these two vector, so the result will be x1 plus y1, x2 plus y2, and x3 plus y3. So in this case, you will be adding the x component of vector A with the x component of vector B, and similarly for y and z component of both vectors. So now we'll be going to the geometric method. So we'll be studying how this geometric method works. So for that, let me draw two vectors. Let me draw it again. This is my first vector. Now I'll be drawing the second vector. So now if you can see here, so these are my two vector. So suppose this first vector is called vector A and the second vector is called vector B. And this vector A has the component 2, 3, and the vector B has the component 2, 1. So now I want to add this vector but geometrically. So in that case there is a method called tip to tail rule. Okay, so if you can see the title here, it is called tip to tail rule. So in this case what you will be doing, just for now I am copying this vector. Okay, so that is vector B. So I have copied this vector and I will be taking this vector and putting it on the head of vector A. So if you can see here, this vector, the copied vector, okay, so it has the same direction as the vector B. Okay, but we have changed only the position of this vector. So if you can see here, in this case, where this vector ends, if you want to find out, so as per you see here, this vector has, position vector has the component 2, 1. So in that case, we'll be counting 2 units in the right direction on the parallel to x-axis, that is 1 and 2, and we'll be counting 1 unit in the upward direction. Okay, so now my resultant vector will be the vector starting from origin, okay, and it ends at this point, okay, where this copied vector ends. So in this case, if you can see here, the resulting vector components will be 4, 4. The x component is 4 and y component is 4. Okay, so what we did is we just take a copy of vector B and put it on the head of this vector A. So where this copied vector ends, that coordinate will be that point. Okay, that point will be the vector component of this resulting vector. So if I perform the addition using the algebraic method for this two vector, okay, so it will be like this: vector A plus vector B. So I am adding the component of vector x component of vector A and B. So it is 2 plus 2 and 3 plus 1. Okay, so my resulting component is 4, 4. Okay, so algebraically you got this answer, okay, using the vector addition, and you can also get the same answer using the geometric method. Yeah. So now we'll be exploring another method called parallelogram method, used for the vector addition. So I am drawing one vector here, starting from origin. So for example, this is my vector, okay, and I'm drawing another vector here. Yeah. So these are my two vectors. So I will using the same way, but here I will be copying two vectors, okay. So first of all, let me write the vector components. So for this vector, the vector components are 3, comma 1, and for this vector, the vector components are 1, comma 3. So let me denote this vector as vector A, and this is my vector B. So now I will be copying this vector, okay. I will be first copying this vector B, same way, okay, and I will be putting this vector on the head of this vector A. Now I will be copying vector A, okay, and I will be putting it on the head of vector B. Okay, so you can see a parallelogram is created. Now my resultant vector will be the diagonal of this parallelogram. Okay, so the resultant vector is a diagonal of this parallelogram. So here you can see here the vector components will be the x component is 4, and my y component is also 4. So this is the parallelogram method. Okay, yeah. So now we'll be studying about the vector subtraction using the geometric method. So for example, uh, I will be drawing the same vector again. Okay, so for example, this is my vector A, and this is my vector, okay, in the third quadrant. So if I write here the vector components, so for this vector A, my components are 3, comma 3. So x component is 3, y component is 3. And for suppose for example, for this vector, that is vector B, my components are x component is -4 and y component is -3. Okay, so in this case, if you can see here, my x component, sorry, vector A is 3, 3, and my y component, sorry, vector B is 4, 3. So if I multiply minus here inside this vector, okay, it will be -4 and -3. Okay, so that's why I drawn the -4 and -3 vector here, that is in third quadrant. Okay, so I want to figure out what will be the vector subtraction. Now if we like go in the same way as the vector addition, so this will be my vector subtraction. 3 minus 4 and 3 minus 3. Okay, so this will be -1 and 0. So this will be my resultant vector using the vector subtraction. Now I want to find out how to do vector subtraction. So using the geometric method. So this was my algebraic method. So I want to figure out using the geometric method. So what I will be doing, I will be counting, okay, -4 and -3 units. So for the minus, we'll be counting on the left side, on the uh, parallel to x-axis, okay. So 1, 2, 3, 4. And for y component, I will be counting downward because it is a negative, so we'll be counting downwards, okay. So this will be 1, 2, and 3, okay. So this is the point, okay. So my vector, if you can see here, my vector lies on the x-axis, okay. My vectors lie on the x-axis, so it has the y component 0, if you can see here. So my resultant vector will be having the vector component -1 and 0. Why 0? Because here on the x-axis the y is 0, okay. So that's why my vector component is -1, 0. So yeah, so you can understand how we perform the vector addition and vector subtraction. For the vector subtraction, actually we count in the opposite side, okay, compared to vector addition. In the vector addition, we were moving on the right side of the x-axis, parallel to x-axis, and for the y component, we will be means we will be moving in the upward direction. But for the negative vectors, okay, for the negative value, if the x component is negative, in that case we'll be counting towards the left, okay, parallel to x-axis. And if the y component is negative, then we'll be counting downwards, okay, in the downward direction. Yeah, so yeah, that's was the vector subtraction. Now let's see the scalar multiplication. So if you can imagine what is a scalar, so the meaning of the scalar is scalar can be any number. It can be 1, 2, 100, any number in the infinite range, okay. So for example, this is my vector, okay. So this is my vector, say it is vector x, and it has the component 2, 2. Now I want to perform the scalar multiplication. So how I'll be doing the scalar multiplication? Suppose I am multiplying 2, okay, into vector x. So it will be 2 by 2. So the scalar will be multiplied with the each vector component. So in this case, my resulting vector will be 4, okay. So now if I 4 comma 4, okay, so x component is 4 and y component is 4. So let me draw another vector, okay. So this is my resulting vector, that is having component x and y component is 4 comma 4. So can you spot one difference here? Yeah, so if you do the scalar multiplication, in that case we are not changing the direction of the vector, okay. So here this 2 comma 2 was a position vector, and by multiplying it with scalar, so the only the change that we can see here, it is in the magnitude of this vector, okay. So you can see here the length of my vector got increased, so it almost double the size of the original vector. So my original vector was 2 comma 2, that is x and y component were 2 comma 2, and the resulting vector, okay, having the x component is 4 comma 4, okay. So it is almost double the size of the original vector, okay. So this is called the scalar multiplication. In the scalar multiplication, we will be adding a number only. The scalar means number, okay. So we'll be adding a number to the vector, and this number will be multiplying, sorry, this number will be multiplying with the x component and the y component. So it is called the scalar multiplication. Now see the dot product. So for example, this is my vector A having the component x1, y1, sorry, x2, x3, and another vector having the component, the vector B having the component y1, y2, and y3. So now in this case, if you can see here, uh, this is my vector A dot vector B. So the dot product is represented by vector A dot vector B. So how will be doing the dot product? The calculation for the dot product is like this. So you will be multiplying the x component of vector A with the x component of vector B, that is x1, y1. Okay. So it is like this: x1, y1. Then you will be doing the addition here. Okay. So after that, you will be doing the addition here. Then you will be multiplying the y component of vector A with the y component of vector B, that is x2, y2. Then again you will be doing the same addition here. Then you will be multiplying the z component of vector A with the z component of vector B. Okay, x3 into y3. So if you can see here, then your value will be the scalar. Okay, so it is a scalar value, means when you do the dot product you will get a number. Okay, in that case there will be no vector component, there will be only a number, singular value, or the scalar value, sorry, scalar value. So let's take one example here. So I have a vector called x having the component 2, 3, 1, and a vector called y having the component 1, 4, 3. Now let me do the dot product here. Vector x dot vector y, it will be like this: 2 comma 1 plus 3 comma 4 plus 1 comma 3. So my result will be 2 plus 12 plus 3. Okay, so the result will be the 17. So when you do the dot product of this vector x with vector y, result will be 17. So there are certain properties of this dot product. Okay, so the first property is called the commutative property. So for that, for example, if vector A dot vector B, okay, so it will be equal to vector B dot vector A. Okay, so if you just reverse the position of this vector, okay, so the result will be same. Okay, whether it's A dot B or B dot A. So this is called the commutative property. Then there is another property. Okay, so for example, that is called a distributive property. So vector A dot vector B plus vector C. So it will be equivalent to vector A dot vector B plus vector A dot vector C. So this is called the distributive property. Now suppose if you multiply the same vector, okay, so that is vector A dot vector A, so the result will be the magnitude of A square. So result will be the magnitude of A square. And suppose if you multiply 0 with any vector, okay, so if you are multiplying 0 with any vector, okay, so the result will be always 0. So in the dot product we have studied these two properties, that is commutative property and the distributive property, okay. And we can also see if we multiply the two vector, so that will be the magnitude of that vector, square of the magnitude of that vector, okay. And if you multiply 0, this is called the 0 vector, okay. If you multiply 0 with any vector, the result will be always be 0. It is called the 0 vector. Now yeah, so there is also another property called the scalar multiplication compatibility. So in this case, let's see here, this is my scalar k, okay. So I'm multiplying this scalar with the dot product of vector A dot B, okay, which is also equal to k into vector A dot vector B, which is also equal to k into vector B into vector A, okay. So what this is doing here is we are multiplying vector with a number, that is scalar, okay. So before or after the dot product we are multiplying the vector with a number before or after the dot product, okay. So it gives the same result, you can see here it gives the same result. So the scalar multiplication of scalar with the vector only scales the vector magnitude, it doesn't change how both vectors are aligned together, okay. So from this equation you can see here, this is called the vector scalar multiplication compatibility. Scalar multiplication compatibility. Now we can also write the dot product of the vector A dot vector B equal to magnitude of vector B A, sorry, multiply by vector B into cos theta, okay. So suppose that if I want to find the value of the cos theta, so I can write like this, cos theta equal to dot product of vector A, that is A dot B, upon the magnitude of A multiplied by magnitude of B, okay. Now suppose if I want to find the angle between two vectors, okay. So what is angle between two vector? So for example, sorry for the mistake. So this is my first vector, okay, and this is my second vector. Now I want to find the angle between these two vectors, that is theta. So I can write it like this, theta equal to cos inverse, okay, A dot B upon the magnitude of A into magnitude of B. Okay, so this result, okay, the cos inverse of A dot B upon the magnitude of A multiplied by magnitude of B, the result can be in either radian or degree. Okay, so for example, the theta equal to 90 degree or pi by 2 radian. Okay, so my resulting vector will be like this. Okay, so here the angle between my two vectors is 90 degree. So these two vectors are called orthogonal vectors. Okay, so whenever the angle between two vectors is 90 degree, you can call it as a orthogonal vector. And for the orthogonal vector, if you multiply or if you do the dot product of two orthogonal vector, okay, A dot vector B, the result will be always 0. So if you multiply any two vectors, okay, and if you get the result 0, you can say that these two vectors are orthogonal. Yeah, that's it.